Greetings and welcome to Physical Science at Hack. In this video, we will work through the sample problems for Chapter 9 in our textbook on chemical bonds. And you'll notice that these, like some of the ones in the last section, that there's been a difference as we've switched from the physics side of the course to the chemistry side of the course. Back in the physics section, there were lots of calculations involved. Here in the chemistry section, we're doing fewer calculations, and there's other types of problems that we will be looking at. And these are quite similar to the ones that we did in the last section for Chapter 8. So let's start here looking at our first question, which asks us to use electron dot symbols to predict the formula of the ionic compounds formed from the following. So we're going to look at the first one here, which is potassium and iodine. So the first thing to do is to write down the electron dot formula. So for A, we have potassium, which has one electron in its outer shell. And we have iodine, which has 7. So as we count those, 1, 2, 3, 4, 5, 6, and 7. Now this makes it very easy to combine because the one electron here can then combine with the empty space in iodine, and that simply gives us potassium iodide, Ki. Now, so that's the first one, and that's all you need for the very first problem here. So let's move on to the second one that we want to look at here. So for B, we have now strontium, Sr, and sulfur, capital S. Now, strontium has 2 electrons in its outer shell, so we can write the electron dot notation there for strontium. Sulfur has 6, so we can count those out, 1, 2, 3, 4, 5, and 6. So again, like with the last one, we have 2 electrons and 2 empty spaces. So this one can combine over here. This one can combine here. And that gives us that all we need for this is one element of each. There's nothing else that's required. So the answer would be SRS would be the chemical formula that we would predict for this based on the electron dot configuration. Now let's look at 2 that might be a little more complex. Let's look at C here. C has sodium and oxygen. So we have sodium Na and oxygen O. Now sodium has 1 electron in its outer shell. So there's the electron dot configuration for sodium, 1 electron. Oxygen has 6, just like sulfur. So we can put those 6 in, 1, 2, 3, 4, 5, and 6. So now what we notice is that sodium has 1 electron in its outer shell, but oxygen needs 2. So what we're going to need to do for this is to have 2 sodium atoms. We can't just get by with just 1 because this extra electron can go here, but then we need something here. We need another one to go here. And that would mean that we'd need another sodium atom. So we could make a second sodium atom with 1 electron, and then that electron would be able to go into the missing space that we need. So that electron would then go in here, and that would mean that we need 2 sodium atoms per oxygen atom in this compound. So what would that give us? Well, if we put those together, we would then get Na. We need 2 of them, so we put the subscript 2 and then O. So this one would be 2 sodiums and 1 oxygen. Na2O would be the compound, the formula that we would get for this compound. Now the last one we want to look at, D here, has aluminum here and oxygen. Now we just did oxygen. Oxygen had 6 electrons. So let's put those in here, 1, 2, 3, 4, 5, and 6. So it has 2 open spaces. Aluminum has 3 electrons in its outer shell. So 1, 2, 3. So this one is a little more complex, because if we take just one aluminum here, well, let's see what we can start out doing. And we can put this electron can fill this shell. This electron can fill this shell, but we have one electron left over. So we then need another oxygen atom. So let's go back and add in an oxygen atom here. So a second oxygen atom, 1, 2, 3, 4, 5, and 6. Now we can put one of those aluminum electrons in it. So we can take this electron and put it in oxygen there, but now we have an extra space in the oxygen atom. So we need another aluminum atom to keep working this. So let's add one more aluminum atom. Again, like all the others, it's going to have 3 electrons in its outer shell. And we can then take one electron to fill this shell. And again, we still have 2 aluminums left over. So we continue the process one more time. Let's add one more oxygen atom to this. And oxygen atom was 6 electrons, 2, 3, 4, 5, and 6. And now if we note, we will have just 2 electrons left over in aluminum. So we can take this one to fill this empty spot. We can take this one to fill this empty spot. And that will leave us with the formula in this case of Al. We have 2 of those. So Al2. And we have 3 oxygens. So Al2O3 would be the formula that we would get in this case for aluminum and oxygen. So let's move on to our second question here. And in the second question, we are actually naming some polyatomic ions. To do this, you would actually use your textbook, and you would use your textbook table 9.3. So you will need table 9.3, and all you need to do in this case is to be able to find these specific polyatomic ions in that table and find their names. And what you'll find if you do that is the following names. So let's put those answers here in red. You would find that OH negative is hydroxide. You would find SO3 doubly negative is sulfite. You would find ClO with a negative as being hypochlorite. We have NO3 negative, which is nitrate. We have CO3 with 2 negatives, which is carbonate. And we have ClO4 with a negative, which is perchlorate. So these, you really just need the table. You go to your table in the textbook and you can pull out those directly. And you will learn some of these as you go through some of the different other problems here. You will get to learn some of them and probably recognize some of them very easily. Others you will still need to find yourself referring back to that table, I am sure, many times to remember all of those names. So on to our third question then. Our third question in these sample problems says to write formulae for the following covalent compounds. So once again, we're going to need a table here, and in this case we're going to need table 9.7. And table 9.7 will help you with learning what these different values are. We need to learn 2 different things. We need to learn the prefixes, with mono meaning 1, di meaning 2, tri meaning 3, and so on. And we also need to learn some of the other terminology that's used when you're for the first element in the compound, you write out its full name. For the second one, you write it as a ide, so chloride or oxide. So chloride would be chlorine, oxide would be oxygen. So let's take a look at a few examples here. In the first one, how many carbon atoms do we have? Well, if you look at the table, it doesn't tell you. And what that means is that for carbon in the very first atom we put in one of these compounds, we do not note how many if it's just one. So instead of writing monocarbon tetrachloride, we just write carbon tetrachloride. So when there is no prefix for the first one, it just means that there's one. So you could write the formula just with the C. Tetrachloride, well, if we look up tetra means 4. So this here means 4. And that means we have chloride as Cl, so that's Cl4. CCl4 would be carbon tetrachloride. Now in second one, in dihydrogen monoxide, again, di means 2, mono means 1. We do use the 1 when it's in the second element. So dihydrogen monoxide would be 2 hydrogens, H2, and 1 oxygen, so H2O, and hopefully you recognize that as water. The third one, we have manganese dioxide. So manganese, again, there's no prefix on it, so it means there's just one, Mn. Dioxide means oxygen, and di means 2. So 2 oxygens, 1 manganese, and you get manganese dioxide as MnO2. The fourth example is sulfur trioxide. Again, we have no prefix, so it's just sulfur. Trioxide, tri means 3. So 3 oxygen atoms, and that's just SO3. And that would be sulfur trioxide, SO3. Dinitrogen pentoxide, our fifth example. Now we have a prefix. Di means 2. Pent means 5. So it's nitrogens, 2 nitrogens, and 5 oxygens, or N2O5 would be the formula for dinitrogen pentoxide. Our last one here is diarsenic, which again, di means 2, and pentasulfate. Pentasulfate again means 5. So this would be diarsenic would mean As2O, sorry, not O, that would be S5. So As2S5 would be diarsenic pentasulfide. So again, you just need to use this table. Will help you as you get started with these. You will much quicker hopefully learn these, so you'll be able to know that di is 2, tri is 3, etc. You'll learn those, I hope, relatively quickly. Now the next problem, our fourth problem here, kind of works these backwards. So now I'm going to give you the formula and you have to write out the name. Once again, we are going to use the same table. This is table 9.7 in the textbook. So again, we're going to table 9.7. And we have in the first one a carbon atom and an oxygen atom. Well, since there's only one carbon, we don't write it as monocarbon, we simply write it as carbon. Now the second one, we have one oxygen atom, so it is going to be carbon monoxide or monoxide. So CO is simply carbon monoxide, one carbon atom and one oxygen atom. Our second example also only has one carbon atom, so again it's carbon to start out, but now instead of monoxide, it is 2, and if you recall, 2 uses the prefix di, so it would be carbon dioxide. The third example again has carbon, so we're doing a lot of carbon here, and it has 2 sulfurs. So we're going to write di again, because 2, just like in this example, 2 meant disulfide. So carbon disulfide. Now here we change things up a little bit in the fourth example. Now we have 2 nitrogens. So again, the 2 means di. We're doing a bunch of those here at the beginning. So this is going to be, now we will put the prefix in because it's not just 2, and it's going to be dinitrogen. We write out the whole name of the element. And then we have one oxygen. So one oxygen would be mono, so dihydrogen monoxide. And we shorten that to dinitrogen monoxide. So again, we look at that too. We have to find out what that means, and we use di as that prefix. One, if there's nothing written, it's a 1, and that means we use mono. In this case, it becomes monoxide. Now our next example involves P4S3. So this is phosphorus, but it's 4 phosphorus, and 4 means tetra. 4 is represented by tetra. So this is going to be tetraphosphorus. And it has 3 sulfurs here. 3 sulfurs means tri. So it's going to be tetraphosphorus trisulfide. Now finally, our last example here has 2 nitrogens, which was di, and 3 oxygens, which was tri. So again, we start off with a dinitrogen and a trioxide. So dinitrogen trioxide again, and you're using table 9.7 on all of these to get your answers. That is going to show you where the prefixes are, and it's going to remind you exactly what you need to use for these. Now the last problem in this section actually does have us do a few calculations on this. So let's take a look at these here. Okay, so let's look at the last one. Now the last example does involve a little bit of a calculation. And we are going to predict whether the bonds formed between these pairs of elements would be ionic, or would they be covalent or polar covalent. So we're going to look at those 3 examples here as to what you could get. So they could be ionic, polar covalent, or covalent. And to do that, we have to do a calculation, and we have to get a set of numbers out of our textbook. And again, we'll need to use a table here, and in this case we're going to use table 9, 10. And you will need this because these numbers are not something you're going to be able to memorize very easily. It includes the entire periodic table. So you're not going to be able to remember these different values for each of these objects, but you will be able to reference these. And if you needed these for an exam, of course, you have reference to your table here. And this table is the table of what we call the electronegativity values for each element. And depending on the range, if you look at table 9.5, which you'll also need, and I should have said this is actually figure 910, not table. So figure 910, it's a periodic table that has these values in it. Table 9.5 below it in your textbook tells you what the electronegativity differences are and what kind of bond that means. So an ionic bond has a difference of 1.7 or more, so greater than 1.7. A covalent bond has one of 0.5 or less, so less than 0.5, and anything in between gives you a polar covalent bond. So let's look at the values that we have here. So for this first one, we have silicon. Well, silicon has a electronegativity of 1.8. So Si is 1.8. Oxygen is 3.5. And what we need to do is subtract those. So 3.5 minus 1.8 equals 1.7, which means this is going to be ionic because it is greater than or equal to 1.7. And I should have said, I said greater than 1.7. It's actually greater than or equal to 1.7. Our second example looks at oxygen. Oxygen, we just found from the previous one, has an electronegativity of 3.5. To find the difference, it's 3.5 minus 3.5, which is 0, and that means it's going to be covalent. Any compound containing the same atom, so oxygen and oxygen or any other atom, is always going to be covalent because the electronegativities are going to be the same. Our third example uses hydrogen, which has an electronegativity of 2.1, and tellurium, which also has an electronegativity of 2.1. So if they're the same, we know that 2.1 minus 2.1 is 0, and we're going to get a covalent bond. Fourth example uses carbon and hydrogen. So carbon has an electronegativity of 2.5. Hydrogen, we just said from the previous, is 2.1. 2.5 minus 2.1 is 0.4, which again gives us a covalent bond. Our fifth example uses lithium, which has an electronegativity of 1.0, and fluorine, which has an electronegativity of 4.0. So if we then use those two and we take 4.0 minus 1.0, we get 3.0, which is again greater than or equal to 1.7, making it ionic. Our last example is barium and sulfur. So barium has an electronegativity of 0.9. Sulfur has an electronegativity of 2.5. 2.5 minus 0.9 equals 1.6, which is less than 1.7, meaning that this is actually a polar covalent. So in this case, you use the table, you use the periodic table in 910 to figure out what the electronegativities are. You subtract them. It doesn't matter which one. You always take the bigger one minus the smallest. It does not matter which order you subtract them. You're just looking for the difference between the two. And you just compare that to the values given in table 9.5. And if they're greater than or equal to 1.7, they're ionic. If they are between 0.5 and 1.7, they are polar covalent. And if they are 0.5 or less, it is a covalent bond. So that concludes our work on the sample problems for Chapter 9 in the textbook. We'll be back again next time to continue on to the problems for Chapter 10. So until then, have a great day, everyone, and I will see you in class.